The advances in technology that would lead to the PET scans we have today began in the 1920s with the discovery of positrons and artificial radiation. In 1929, the invention of the cyclotron allowed for particle acceleration. In the 1950s, the first cyclotron was installed in a medical center. The invention of scintillation detectors allow for luminescence and materials excited by ionizing radiation to be recognized. The later development of positron detection tomographs and the synthesis of the radioactive compounds we use today, as well as the use of self-shielded negative cyclotrons, allowed for the PET scans that we use in modern medicine. Before undergoing a PET scan, the patient is injected with a radio-labeled tracer. This tracer is created in a cyclotron by accelerating particles to very high speeds and focusing them on a target substance. The accelerated particle and the target substance are specifically chosen to produce the desired radioactive element for the structure being visualized. For example, tumors are visualized with radio-labeled glucose. The more brightly the tumor presents, the more metabolically active and invasive it is. As the radionuclide in the tissue decays, it produces positrons, which leads to the emission of gamma rays. These gamma rays are detected by the positron emission tomography scanner and can be analyzed by a computer to generate 2D or 3D images of the tissue or organ being visualized. Today, PET scans are most commonly used in oncology, cardiology, and neurology, but as technology advances, their uses are expanding. The primary components of PET scans, and the ones that have improved the most as technology advanced, include the scintillating component that detects gamma rays and produces the electrical signal interpreted by the computer, the compound used to radioactively label tissues, the PET scanner itself, and the use of PET scans in conjunction with MRIs and CT scans to improve imaging technology. This is a scanning electron microscope image of a scintillating component that allows for the detection of gamma rays. Today, the most commonly used scintillating component is bismuth germanate, but cerium-doped lutetium oxy-orthosilicate is showing considerable promise as a scintillator due to its high effective atomic number and its rapid decay. It is currently very difficult to produce, but in the future it is likely that this will replace bismuth germanate and improve the images gained by PET scans. New radioactive tracers are being developed that will allow for very specific targeting of metabolic processes and molecules within our bodies, improving the diagnostic ability of future PET scans. New scanners are being developed that allow for full body imaging. Currently, PET scans take a very long time and are associated with an extremely high cost. These scanners will allow for an increased axial field of view, increased sensitivity, and a significant cost reduction by producing more images in a much shorter quantity of time. Faster scanners and multi-slice detectors are also being developed, which will allow for 4D imaging and can be used for things such as coronary angiography, which was previously an invasive procedure. This is bismuth, one of the primary components of bismuth germanate used in the scintillating detector of PET scans today. Bismuth is found in makeup to increase shine, Pepto-Bismol to drive fluid and electrolytes into the bowel, and combined with other metals like lead, tin, or iron to produce alloys with low melting points that can be used in fire detectors and extinguishers. Bismuth is found throughout the Earth's crust in bismuth sulfite and is usually obtained as a byproduct of lead, copper, tin, silver, and metal refining. It has been known since the 14th century but was thought to be a component of lead due to its similar properties. It was not discovered as an individual element until 1753 by Claude Joffre. Today, bismanol, an alloy of bismuth and manganese, is a permanent magnet of high coercive force. It is used in small motors. The bismuth metal is being used as a replacement for lead in shot and bullets, and bismuth is being used in nuclear reactors and to make transuranium elements using cold fusion. Prior to 2003, it was believed that bismuth was the heaviest element that still had a stable nucleus. However, it was discovered that bismuth does decay into thallium, but its half-life is about 20 billion years. Recently, bismuth won the half-life record for alpha decay.